Hi dear students, welcome back to the lecture series on topology second. In this lecture we are going to prove a very important theorem, that's the Urysohns lemma. So first of all I will state this lemma. It states that let X be a normal space. Let X be a normal space. Let X be a normal space, and let A and B be two disjoint closed subsets of X, and let A and B be two disjoint closed subsets of X, closed subsets of X. Then there exists a continuous real valued map. Then there exists a continuous real valued map F from the normal space X to the closed interval 0, 1, such that this F, it maps each point of A onto 0. F of A is equal to 0, and it maps each point of B onto 1. Okay. So here X is a normal space, and these are two disjoint closed subsets of X, A and B. And here it's a closed interval, say 0 to 1, it's a closed interval 0, 1, and it's a map from X to 0 to 1 interval, and it maps each point of A onto 0. So image of every point which is in A is 0, and image of every point of B is 1. So that's the statement of this lemma, Urysohns lemma. Before proving this lemma, I want to recall, before proving this Urysohns lemma, I want to recall the lemma number 2 of previous lecture. Lemma 2 of previous lecture, which states that if X is T1 space, or you can say X is a normal space, it states that X is normal space, X is normal space, X is a normal, it states that X is a normal space if and only if given any closed set A, given any closed set A and an open set U, such that A subset of U, then there exists an open set, then there exists an open set, then there exists an open set V, such that A subset of V closure subset of U. That's the lemma number 2, which we have proved in previous lecture. X is normal space if and only if given any closed set A and an open set U, such that A is subset of U, that means U is a neighborhood of A. There exists an open set V, such that A subset of V closure subset of U. Now here we are given that X is a normal space and A and B are two disjoint closed subsets of X. So we can apply this lemma. Since A and B are closed subsets, disjoint and closed subsets of X, therefore A must be subset of B complement. In other words, B complement is an open set containing A. So that's we can find an open set V with this property. So let's prove this lemma. Since A and B are disjoint closed subsets of X, they are disjoint closed subsets of X. So therefore A is subset of B complement. X a normal space, A and B, they are disjoint closed subsets of X. So that means A is subset of B complement. B complement is this whole space outside of B, this shaded region. So that means this A is subset of B complement, which in other words it means that B complement, since B is a closed set, therefore B complement is an open set. So that means B complement is an open set containing A. And here we have seen that this if X is normal space finally given any closed set A and any open set U containing A, then there exists an open set V such that A is subset of V closure subset of U. So we can apply this lemma. We can say there exists an open set, thus there exists an open set. So we denote this open set by U1 by 2 such that A subset of U1 by 2 subset of U1 by 2 closure, then subset of B complement. So that's this lemma actually, okay? Lemma number 2. Now U1 by 2 and these two, U1 by 2 closure, these two, it's a closed set, and B complement is an open set containing this containing this closed set U1 by 2. So therefore for this pair, the closed set and an open set containing the closed set, we can find an open set. Say let's denote that open set by U3 by 4 such that this condition holds, that closed set is subset of the open set and open set is subset of its closure, then closure is subset of B complement. So for this pair, and for this pair we have one more pair. This A is a closed set, U1 by 2 is an open set containing A. So for this pair again we can find some open set. So since A is subset of U1 by 2, so therefore there exists an open set. Let's denote that open set by U1 by 4 such that A subset of U1 by 4 subset of U1 by 4 closure and subset of U1 by 2. So again, since again since U1 by 2 closure is a closed set and it is contained in the open set B complement, so therefore there exists an open set. Let's denote that open set by U3 by 4 such that this closed set U1 by 2 closure is subset of the open set U3 by 4, and which is a basis subset of U3 by 4 closure, and that subset of the open set B complement. So that means we have this this A subset of U1 by 2, A subset of U1 by 2, which is subset of U1 by 2 closure, and that's subset of U1 by 2 closure. A subset of U1 by 2, U1 by 2 subset of U closure, U1 by 2 closure, and U1 by 2 closure subset of U3 by 4, subset of U3 by 4, which is subset of U3 by 4 closure, and U3 by 4 closure is subset of B complement here. A subtract u1 by 2, u1 by 2 subtract u1 by 2 closure, and u1 by 2 closure subtract u3 by 4, u3 by 4 subtract u3 by 4 closure subtract B complement. So if we continue this process for each such number, these numbers are called didactic rational numbers. The number of the form of this m divided by 2 power n, m divided by 2 power n, where n is any number, n is greater or equal to 1, and m varies from 1 to so on up to 2 power n minus 1. 2 power n minus 1. These such rational numbers are called didactic rational numbers. Suppose, for instance, if we take n equal to say 3, then what are the values of m? They are 1, 2, so on up to 2 power 3 minus 1. The values of m are 1, 2, 2 power n minus 1. If we take n equal to 3 here, then the values of m are 1, 2, up to 2 power 3 minus 1. That means they are 1, 2, 2 power 3 is 8, 8 minus 1 is 7. So these numbers, say 1 by 8, because it's 2 power n is 3, 1 by 8, 2 by 8, 3 by 8, up to 7 by 8. They are didactic rational numbers. And in this case, for this sequence 1 by 2, 1 by 2, 3 by 4, 3 by 4, in this case our n is 2. N is 2. So values of m are 1, 2 power 2 minus 1, that's 4, 1, 2, 3. So they will be 1 by 4, then it's 2 by 4, then 3 by 4. These three numbers, 1 by 4. Okay. Sorry, it's here a substuff u1 by 4, which is substuff u1 by 4 closure, that is substuff u1 by 2. Sorry, mistake, it's a 1 by 4, a substuff 1 by 4, which is substuff 1 by 4 closure, and 1 by 4 closure is substuff u1 by 2, u1 by 2 subtract u1 by 2 closure, u1 by 2 closure is subtract u3 by 4. So it is subtract u3 by 4. So for each such step, we have a sequence set up, say, a collection of these didactic rational numbers 1 by 4, 1 by 4, then 3 by 4. Okay. These are didactic rational numbers. Okay, or if you want to insert these sets also here, say it's u1 by 2 here, so I can write it as a subset of u1 by 4 subset of u1 by 4 closure, which is a subset of u1 by 2. u1 by 2, it's actually 2 by 4. u1 by 2. Okay, u1 by 2 is subset of u1 by 2 closure, and u1 by 2 closure is subset of u3 by 4, which is subset of u3 by 4 closure, that is subset of B complement. So that's this is the they are didactic rational numbers 1 by 4, 1 by 2, then 3 by 4, 1 by 4, then we have 2 by 4, 2 by 4 is equal to 1 by 2, it's 1 by 4, 1 by 2, 3 by 4. So if we now we continue this process, if we continue this process, for each didactic rational number, for each didactic rational number of the form t equals m divided by 2 power n, where n is greater or equal to, it's any natural number, but m is 1, 2, up to 2 power n minus 1. So you can easily see that these numbers, they lie between 0 and 1, because m varies from 1 to 2 power n. It is at most 2 power n minus 1. So that means numerator is less than the denominator always. So they are the numbers lying between 0 and 1, didactic rational numbers. Okay. Then we have since for any two didactic rational numbers, say if I choose any two direct rational numbers, say, and then such that for any open set, such that for any didactic rational number, you can say didactic rational for any didactic rational numbers t1 and t2, we have this: if t1 less than t2, if this didactic rational number t1 is less than the didactic rational number t2, we must have this condition. First we must have ut1, which is subset of ut1 closure, and then we have ut2, which is subset of ut2 closure. This is always true. ut2 closure. A subset of ut1, subset of ut1 closure, subset of ut2, subset of ut2 closure, and finally it is subset of B complement. Like here, this 1 by 4 is less than 3 by 4. So A subset of u1 by 4, subset of u1 by 4 closure, which is subset of u3 by 4, subset of u3 by 4 closure. This is true for any didactic rational, because we have constructed this sequence in a way that it satisfies this property. Whenever we have two didactic rational numbers t1, t2, such that t1 less than t2, then this satisfies this inclusion. A subset of ut1, subset of ut1 closure, subset of ut2, subset of ut2 closure, which is subset of B complement. Now we define a map based on these didactic rational numbers from X to R. Define f from X to R by f of X is equal to 0 if X is in every ut, if X belongs to ut for every didactic rational number. It is in u1 by 2, u3 by 4, every number, u1 by 4, every didactic. For any didactic rational number t, X belongs to ut. So it is in u by t. This t is a didactic. It is m divided by 2 power. It is in every ut. We take its value as 0, and it's equal to supremum of those t's such that X is not in ut. We take all such t's such that X is not in ut, then we take the supremum of such t's. So clearly, since these didactic rational numbers, they lie between 0 and 1, therefore this supremum is also lies between 0 and 1. It's either 0 or 1 or in between 0 and 1. And here its value is 0. So that means there one can easily clearly f of X belongs to the closure interval 0, 1 for all X belongs to X. So that is f is a function from X to the closure interval 0, 1. X to this interval 0, 1. Now we see that it maps this function. It maps each point of A onto 0. So let's choose any point of A. Let X belongs to A. Whenever X belongs to A, here you can see this. Whenever X belongs to A, then it is in every ut, because each A is this A is subset of each ut actually. So this means that X belongs to ut for all t. And whenever X belongs to ut for all t, it implies that f of X is equal to 0. So therefore f maps each point of A onto 0. So which in other words we can say f of A is equal to 0. Now second, if X is in B, let X belongs to B. If X is in B. If X is in B, then we show that its value is 1 if X is in B. If X is in B, so it means that X is not in B complement. So it means that X is not in B complement, so whenever X in B, so it's not in B complement. Whenever X in B, here we show that we need to show that its value is 1. So actually we have to find the points whenever X is in B. So it means that X is not in A clearly. So because A and B are disjoint, this means X is not in A. X does not belong to A. X does not belong to A. So it means that if X is not in A, because A and B are disjoint, you can see A and B are disjoint here, sets, they are disjoint sets, so X is not in A. Whenever X is not in A, it means that X is not in any UT, because A is subset of each UT. So which means that X does not belong to UT for all T. And the supremum of these T is, because T is now any didecretional number and its supremum is 1. You can see here it's m by 2 power n. If it's the maximum value here for this choice of m and n, it's here 2 power n minus 1 divided by 2 power n. And what's the you can see its supremum is 1. If n is approaching to infinity, it will be equal to 1. So then f of x, which is equal to supremum of T is, where T is didecretional number, it's m by 2 power n, where n is any number, m runs from 1 to 2 power n minus 1. This supremum is obviously it's equal to 1. You can easily verify it. Its supremum is 1. So this means that f of B is equal to 1. This implies f of B is equal to, because it maps each point of B onto 1. So this proves the that requirement that it maps each point of A onto 0 and each point of B onto 1. Now we just need to show that it's continuous. Now we prove f is continuous. Now we show that f is continuous. F is continuous. And here this f is a map from x to the interval 0, 1, and by continuous we mean that inverse image of basic open sets open, because we know that the map between the topological space x and y is continuous if and only if inverse image of sub-basic open sets is open. Sub-basic open set. The actual definition is that inverse image of every open set is open, but we have already shown that, or in the previous semester you have seen that the map between the topological space x and y is continuous if and only if inverse image of sub-basic open